Good afternoon, everyone. Welcome to the Full Spectrum series. I am Nick Valentino. I'm an academic counselor and your host for this series. The Full Spectrum series is composed of introductory lectures from our Hajim faculty and staff. This is an opportunity to ask Hajim faculty about their program, their research, and the types of challenges engineers in their field work to solve. If you can't stay for the whole program, that's okay. These videos will live on the Hajim School Facebook page and YouTube and Instagram. If you'd like a chance to win a prize, please put your name in the chat or the Facebook broadcast and indicate whether or not you're a prospective student, alum, current student, faculty, or any other part of the university community. During the lecture, I'll be monitoring the chat on Zoom and Facebook for questions, and we'll have time for questions at the end. This session is presented by Dr. Thomas Howard. Professor Howard is an assistant professor of electrical and computer engineering. Dr. Howard directs the University of Rochester's Robotics and Artificial Intelligence laboratory. He holds secondary appointments in Department of Computer Science and Department of Biomedical Engineering, and is a member of the Goergen Institute of Data Science. Professor, let me know if I got any of that wrong, and I'm turning this over to you.
All right, sounds good. Thanks for the introduction. So today I'm really here to talk about the electrical and computer engineering program. But I guess a little more background on me. So I started here about 5 years ago as junior faculty. I came here via MIT. I was at the Computer Science and AI lab there for several years. I worked at NASA Jet Propulsion Lab a few years prior to that. My PhD formally is in robotics from Carnegie Mellon, but I actually come from here academically. I was a double engineering major here back in the early 2000s in electrical and computer engineering and in mechanical engineering. So it's great to be able to come back and actually join a program that I was also on the other side of at one point. So I'm a roboticist. I do experimental robotics. I work on getting robots to do things safely, accurately, effectively out in the real world. I do a lot of work on human-robot teaming, trying to get robots to be effective human partners. But a big vein of my research is in trying to make sure that these things work for real. I'm an experimentalist. We use lots of different robots. I'll show some robots from my lab later on. But the images down there on the bottom are kind of snippets from all of my past work back as an experimental roboticist for about 17 years. But here I'm really going to talk about ECE in general. So ECE is a pretty broad set of topics. We interact with people who develop things from electrical engineering backgrounds all the time. We can thank lots of modern computing and lots of the kind of devices we work with any day, thanks to the work of electrical engineers. So I tend to think about kind of two scales of electrical engineering. We go all the way from the quite large to the very small. On the large end of things, we tend to think about things like electrical grids and robotics. So there's a picture of one of the robots there from my lab on the left. We do control systems. We build layers of artificial intelligence. It's really about embodied artificial intelligence, as opposed to kind of broad AI, which does not necessarily require that embodied component. So I don't know if anyone joined for any of the CS talks. Robotics lives in ECE here in the sense that we are doing embodied intelligence that needs to deal with the physical world and sense it. As we move down that scale, we think about sensor development, we think about signal processing, we think about computer architectures, and then we get all the way down to the individual devices and transistor level. We develop and we work on semiconductor physics. If you want to develop next generation chips, a background in electrical engineering is needed and required. And considering the interest, actually, even at a number of different scales, including robotics, because I see this in my own field as well, there's this renewed interest in developing custom chips for solving problems. So I think it's a really interesting time in electrical engineering, and it's great to have a program here at Rochester that does this. So there's a number of different topics in ECE. I'll talk about the way our program is structured later on today. But I tend to think about kind of 5 subdivisions of ECE within our program. We have concentrations and tracks in signals communications. We have a track in microelectronics, think semiconductor physics and devices. We have integrated circuits. So those interested in both, VSLI, very large scale integration, integrated circuits, or other integrated circuit design ideas. We have tracks and classes in that. We also have computer architecture for those interested in how to actually put together these larger systems. And then this new thread in robotics, which I guess I'm at the center of. I just have an image of one of the control systems we were developing for a robotically assisted medical imaging project that we were actually doing in my lab for several years. Okay, so the today's presentation is really set up into three different blocks. The first one is I just want to introduce the faculty and some of the research areas that we work in. Then I'll talk about the undergraduate program, and then I'll talk a little bit about undergraduate research. So we'll go on. If anyone has questions, please do feel free to ask them. I think Nick will send the questions my way if they come up, but please do feel free to ask. Okay, so we have around 20 faculty in electrical and computer engineering. Mark Bacco has been here for quite a while. He was the previous chair of the department. Mark actually has the distinction of being my undergraduate advisor when I was here, but he's an excellent researcher, very well known for work a number of different areas, but including this recent interest in digital audio and music, and has put a lot of work into the founding of our audio music engineering program within the Department of Electrical and Computer Engineering. Mujdat actually came here recently. He is both heading up the data science initiative, which you may hear about later today, is what I understand. And he has a focus and interest in signal processing here in the department. Hanan actually teaches two of our core classes right now, but he also has a research interest in spectronics. But if you've been through our program recently, he has a distinction of both being the professor who you learn probability and statistics from, and being the one who introduces computer architecture. Marvin, who has an interest both in medical imaging and signal and image processing, is currently the ECE chair of our program. He is he also was leading us through this curriculum redesign that I'll talk about coming up in a few slides. Xiao is a relatively new faculty here. I think just switched over to associate, so I think a few years academically older than I. Interested in digital audio music and machine learning. E.B. Friedman is very well known for his work in VSLI, teaches our VSLI courses. I actually worked for E.B. as an undergraduate research assistant here, so I had experience of working with him in the lab, and it's great to have him here on the faculty. We have Mike. Mike is both teaching a number of the AME courses, including some of the design courses, and also has research interest in digital audio and music. We have Wendy. Wendy is both the dean of the engineering school here and still one of our ECE faculty, a well-known expert in wireless network communication and other topics. But it's great to have Wendy still as part of our department. There's of course me, who's Tom Howard. My interest is in robotics, more broadly than just that, but that is where my research interests center. We have Michael. Michael is at the core of the computer architecture work we have here. Michael teaches some of the advanced courses in multiprocess architecture-based approaches. Oh, I see a chat question. Is there a question?
Not at this point.
Okay, fair enough. Okay. Željko is interested both in integrated circuits and in the audio music engineering program. He's actually teaching some of the audio signal processing courses here. Seljuk actually came to us via another university recently, and also joins the work going on here in integrated circuits. We have Robert Levac, who is one of our core faculty here in digital audio music, teaches I think some of our recording classes. Very well known, and those courses get lots and lots of interest. We have Ming Lun, who is both interested in digital audio music, but also has taught our introductory programming courses for a number of years. We have Sean Lin, who teaches advanced courses in some of the device and device physics courses, but is a well-known expert in quantum optoelectronics. In fact, I think one of the recent ECE news stories there in our department is about some of his really interesting recent work. So if you're interested in quantum optoelectronics, I highly recommend going and check it out. Gonzalo is one of our researchers here on signal processing. He also joined around the same time I have, so it's great to see him teach his class. Also teaches a very popular class in random processes, both that lots and lots of grad students have taken that class that I know of and have learned quite a bit. We have Jack Motley, who has taught our introductory circuits classes and senior design for a large number of years. His interest in audio music has research that dates back into ultrasound and whatnot as well, but really a well-known expert for the work in kind of system engineering design, and is one of the go-to people, I think, for anyone who is building devices here in our department. Jack gets lots of interest to students talking to him around senior design days, trying to get their devices to work. So great experimentalist. We have Kevin Parker, who's well known for his work in image processing, medical processing, also teaches some exciting advanced electives, including some recent one, I think, on scientific puzzles, which I have yet to explore myself, but it seems cool. We have Steve Rosner, also digital on music, teaches some of our kind of recording-oriented classes there. We have Garsh Sharma, who has taught signal processing and advanced electives in that topic. We have Sarah. Sarah also teaches some of the senior design classes as research interest in digital audio music. She is, I believe, an alum of this program as well. I think I went to her dissertation defense. Very cool work on 3D audio understanding. We have Roman. Roman is an expert in some of these optoelectronic devices and well known for his waves and our general work in waves and fields. He teaches the waves and field class that we have here, EC 230, and I guess you'll see him in the curriculum later on. And then we have Hui Wu and Stephen Wu. Hui Wu teaches our integrated circuits course, EC 222. And Stephen Wu has also relatively new faculty here, does some very interesting work on semiconductor devices, but also teaches the precursor to the integrated circuits course that Hui teaches, which is the semiconductor devices course. So lots of us have research laboratories. This is an example of what a laboratory looks like. It's actually mine. So this is my robotics artificial intelligence laboratory where we do experimental work with robotics. But if you're interested in any of these individual topics, basically check out the website with descriptions of what their labs are. Often we have links on the website to our individual lab pages that talk about the kind of work we're doing and what kind of publications we have out. So if you're interested or excited about any of this, the website that we have in ECE is a good way to do it. But often you'll find pages like this that'll describe some of the work that's going on. Okay, so I'm going to talk a little bit about the undergraduate program now. So if you have questions about the specific program, again, feel free to ask. We are an ABET accredited engineering program. If you're interested in what goes into an ABET accredited program, feel free to check that information out. But in general, our goal is to develop the next generation of engineers that understand both the theory and practice of electrical engineering. We want students to be able to go off and find good jobs. We also want them to understand the base or the fundamentals of these things, so that way they can have a long and fruitful career. It isn't just about learning the skills for now. It's about it's about trying to make sure that you are provided the proper foundation so as the field continues to evolve, that you have the right background. So that's really our high level mission. We want engineers to go out there, make an impact in the world in a positive way, and also make sure that they have kind of long and fruitful careers. So there's a number of different program objectives we have, in addition to the idea that, our students can go off and solve complex problems and apply, engineering principles to design these things. We also want to make sure that they are effective scientific communicators. Scientific writing, technical communication is an important part of this. The many lab reports that they write for my mechatronics embedded systems this semester, we've been practicing our ability to technically communicate what you did so that you can do clear and concise communication of these ideas. We also want people to enjoy it, and we want people to ensure that they're doing the kind of work which they understand the social implications and kind of their ethical responsibilities for these things. So we have a number of different facets into our program that ensure this, but we have a number of student outcomes that align with these the ABET outcomes that are fairly well known. We want our students to be able to solve problems. We want them to be able to find solutions that reflect on broader impacts of their design choices. We want them to be able to communicate effectively. We want them to understand professional responsibility and their ability to ensure that they're developing safe and effective devices. We also want them to be effective teammates. You're often not going to work in isolation. We have team activities. We have senior design activities that are a lot of fun to go and visit all the design teams, actually demoing what they're developing over the years, but also the other kind of interesting courses that have group work towards the end, and when they have demos, it's actually a great thing to see here in our department. And then the ability to go off and do proper experimental work. I have students right now developing feedback control systems. They're in the laboratory for my mechatronics course, and they're learning the nitty-gritty of actually getting these things to work with real electronics. So that's an important part of it. And we also want them to be able to go out and acquire new knowledge. The ability to do their own investigative work and ensure that as new things develop, they can figure it out, and they know they have the skills and the confidence be able to go off and do these things is an important part. So these are kind of the rough ideas of what we are going off to go do in our program. We have 14 required courses in our program. Not all are 4-credit classes, some are. We have the EC 101 Introduction to Electrical and Computer Engineering class. We take this during the first semester of your time here. Leads into other courses, both on logic design, circuits and signals, and our introductory programming course on C and C++. These are typical pre-major requirements in addition to some math and physics courses that I'll talk about in a little bit. But this is really how you get started with electrical engineering, that gives you a foundation in RLC circuits and logic devices and some laboratory fundamentals that we try to develop in these early courses. As we go on into the second, third, and fourth year, you start taking 200 level classes. We have a number of 200 level classes that represent both the foundations in electrical engineering and opportunities to start specializing in some of these other topics and courses. We teach an entire course in computer organization. This is the course I mentioned that Hajim was teaching before. We have a new revision of a course, EC 216, Mechatronics and Embedded Systems. This is actually evolved from a prior course on microprocessors and data conversion that I took when I was a student. So I actually teach this course. It is a kind of a modern evolution of some of these ideas. We do more work with motors, motor control systems, and really provides a kind of a baseline fundamentals of robotics with a new track that allows you to specialize in that topic here in our department. We have our integrated circuit and semiconductor device sequence, EC 221 and EC 222. We follow that up with EC 230 and EC 240, our waves and signals courses, and then this fundamental course in probability and statistics that I also mentioned teaches EC 270, which was a relatively new addition to our program in the last decade or so. Okay. We also have a capstone design sequence. This both includes our ethics course that we review, ethical foundations of engineering. And then we also have a design seminar and a capstone design sequence. The design seminar is really about trying to choose, identify a topic, and learn systems engineering principles. And the capstone design is where you get to go off and actually implement and demonstrate these ideas. So it's a lot of fun. It typically ends up with the design demo day there over in the athletic center, big gymnasium, but it's a lot of fun to go off and see what people build, and it's exciting to talk to students in our department who were able to choose problems they were actually invested in and want to go off and do these things with. So those are the foundation kind of required classes in ECE. We also have 3 advanced electives, which is kind of a new feature of our program. We used to only have a single advanced elective. We've retooled it to allow students to either choose breadth or depth in the program. I think that the current job market sometimes favors specialization if you know what you want to go off and do, but it also gives that flexibility in case you want to blend interesting things. So often you see students blend a few different specialties together to get unique combinations, which I think is exciting. So one of the areas is in signals, communications, image processing. We have advanced courses here in both digital and wireless communications, signal processing, and introduction to digital signal processing using Python. So that's the dip down there for 247. We have a concentration in integrated circuits, which is both VSLI and the high-speed integrated electronics course. We have a track in computer engineering. This is one of the courses that I mentioned that Michael Wong teaches, multiprocessor architecture. We also have courses in semiconductor devices, waves and fields. Actually, 223 is in both of those because we also have a new track in just semiconductor devices. And we have this new track in robotics, which I teach the courses in both in robot motion planning and a course in mobile robot estimation, mapping, navigation, and interaction. So there's other 200 level courses you can interject into this these advanced elective requirements. We don't have students always take all 3 in the same area. We like to see students kind of disperse them through the topics, but now there's more flexibility to specialize in those courses that you are particularly excited about and want to prepare for what's next after undergrad.
Professor, we have a question I think that it would fit now.
Yeah, sure.
What are some examples of assignments and or projects given in these classes, namely logic design?
Ooh, logic design. So logic design dealt with things like FPGA programming and trying to build simple logic circuits out of Boolean logic gates. So I remember the last time I worked with some of those laboratories, Sometimes we were using discrete logic elements, breadboarding them and building circuits and measuring their, behavior and whatnot. Sometimes we were actually doing programming in things like, VHDL or other programming languages with these other devices so that we get some of these behaviors actually programmed in there. So that's an example of what you might see in digital logic. I actually have some slides later on that talk about some of the assignments and coursework that we have going on in my courses. So I can revisit that question, or if that's enough. Did I answer the question?
It was submitted in the chat. So
okay. Well, if I didn't fully answer the question, I'm happy to revisit it in a couple minutes. But okay. So back to this. So we have a few other requirements in the program. We do require a 4-course sequence in mathematics, the 2 calc courses, a multidimensional calculus course, and linear algebra with differential equations. Differential equations, I like to say, are kind of at the heart of a number of different topics here in electrical engineering. So having that mathematical foundation in DiffEq really matters. We also have a course in physics. So we have a 3-course sequence, both mechanics, electricity and magnetism, and waves in modern physics. We now require waves in modern physics because of the renewed interest or new developments in quantum devices. So we think that having the right foundation there with an understanding of modern physics for electrical engineers who are interested in building those kind of devices is important. We also have additional requirements for upper level writing. That ethics course I mentioned before, we have lots of writing there. And then we have the university's writing 273 requirement. Beyond that, we do require 1 cluster. So we have 1 3-course cluster in humanities or social sciences. This is also balanced out by 2 additional courses in humanities or social sciences that you may have. When I was a student here, I think my cluster was in art and art history. So that was fun to do some things beyond pure engineering, but it was nice to have that flexibility to take the courses I was interested in as part of the cluster. And then there's some additional requirements like credit hours and I am already mentioned the writing 105, the introductory writing course here at the university to satisfy. But this is what a typical path looks like. There is it's a bit of an eye chart, but it is available on the website if you're curious. There is flexibility in the program, which is kind of new, which is nice, is one of our goals for the redesign of the curriculum in recent years, so that we have more opportunities to blend these advanced electives the way you want. But a number of different students, both some of the people switch into the major after a year. We have an on-ramp for doing that, which actually still works. So the nice thing is in the beginning, you're still building the kind of fundamental math and physics background and clusters and whatnot, and taking some of these introductory courses. But when students realize they really want to be electrical engineers, we do have ways to get them in there. So if anyone is interested in transferring in from that point, please follow up with our undergrad coordinator or just send me an email if you can't get in touch. Okay, so we have new things going on at ECE. So I mentioned before this new course in mechatronics embedded systems. We're doing work with PIC microcontrollers, and we actually build like motor control circuits, stepper motors, servo motors, DC motors. We're learning feedback control. We're learning sensor integration. We're doing more C programming applications to the C programming that you're doing. So this is some of the new work that's going on. There's also this new track in robotics that I had mentioned before. The mobile robot estimation navigation class is an evolution of my autonomous mobile robots class that I taught for a number of years, and actually taught a variation of it back when I was a lecturer at Caltech, when I was at JPL working there as well. But you build the whole stack of a robot autonomy architecture and actually get a robot to drive around by yourself at the end of the semester. So we spend a week building a mapping system, a state estimation system, a planning system, a control system. You get all these software modules to work together in this larger architecture. We build a simulator, we put it on physical robots, they drive around. And I like to joke, grade goes down when you start hitting walls, but it's your code, which is the exciting part. It's not a group project for this one. It's by the end of the semester, you've gone from learning fundamentals of robot programming to actually having a fully capable navigation system that you develop by yourself. So this is one of those fun kind of semester-long activities that we do lots of hands-on teaching. I go in and teach the workshops for try to get these things to work every week. And I think it's a lot of fun. I think it's where people really learn either a lot about robotics or a lot about the kind of math that goes into actually getting robots to behave intelligently. which has lots of connections to other parts of electrical engineering. It's the course where undergraduates typically learn Kalman filters and things of that nature. So I think it's a lot of fun, and a lot of students have been through that. Okay, a couple more slides, then I'll wrap up. So a number of students do undergraduate research here in our department. I'm a product of that. I did undergraduate research here, actually all 4 years I was here as a student, 3 years in physics labs with Dan Watson and 1 year with E.B. Friedman doing VSLI work. But we have a number of different students who work in different departments. I have a little sampling of a set of projects that involve undergraduates here at the department. We had work here on sound source sound search algorithms done by some work in Xiao Diwan's lab. This is work that again led to a paper. The idea is you can basically go through and give a sound input, and then you search for kind of an equivalent or similar match. We have other work that went on in Selchuk's lab on trying to investigate or identify side channel attacks, something that those concerned with computer architecture are particularly concerned about, using some modern machine learning techniques. There's some work here on language-guided mobile manipulation. This is actually a student here, Ethan Fonostock from my laboratory. There's a picture of him down there with one of our mobile manipulators from our lab. But we're working on trying to get robots to follow language instructions. So here, if we have microphones on robots, we go tell them to do things in the physical world. The robot has to understand what it is we are talking about, and then how to go off and do it safely. All from live sensor information like LiDARs and cameras and whatnot. So we did some great work, actually published, I think it was on 2 or 3 papers, either as co-author or lead author. And now he's off doing a PhD at MIT after this. We have Lena here did some work with Roman on trying to investigate some semiconductor devices that were concerned with terahertz imaging, terahertz signals. Cool work that was highly experimental and was interested in trying to identify or use terahertz imaging for understanding tissues. But other cool work that, it's actually fun to see the descriptions of student projects for students I've had in classes. So that's always cool. But I'll wrap up here since I think I got my half an hour. So electrical engineering is a pretty broad field. It comes from very large scale things, autonomous robots, and the like, all the way down to kind of the small scale semiconductor devices and trying to get things to work. So if you interact with lots of electronics every day, that's a lot to the product of electrical engineers, and it continues and remains an exciting field. Being here at a research university and being able to engage or take part in undergraduate research and being part of a small department actually works out to be it was a wonderful thing here when I was a student, and it's some of the reason why I've had success myself. And one of the reasons that I actually came here was partly because of this open curriculum, the Rochester curriculum, that allowed me to pursue classes that I was really excited about. Take lots of students I talk to do major minors and things they're excited about, take clusters, take additional classes. I was able to squeeze in a double major in 4 years. It was tricky, but the curriculum allowed me to do it. And I felt like, my course selections were not, I never felt like I was taking classes I really wasn't excited to take. So it was a great thing about the program. That's all I've got here for slides. I'm happy to take questions.
Great, excellent. So feel free to put your questions in the chat. One of the things that I wanted to start with is a question as advisors we get all the time. We have students who are trying to decide between electrical and computer engineering and computer science majors. And besides the difficulty in sort of figuring out which math to take and when initially, what is your thoughts on what students should do if they have these two interests in both hardware and software?
Sure. So there's certainly lots of crossover between the two, right? Like if you look at a lot of job postings for jobs, they're often looking for people with backgrounds that may include both of those degree programs in it. So there tends to be flexibility between that. So you have to think about, which program is best structured for your own interests. Certainly in electrical engineering, you will get more of a hardware-oriented background. There's other additional requirements in ECE that are a bit different in the sense that we require a physics track. We also have a senior design capstone sequence. Those are probably the two biggest distinctions between computer science and electrical engineering here. I actually think that physics and understanding of physics is really important, particularly in the robotics domain that I work in, because we need robots that understand how they interact and kind of move in the physical world, and having that fundamental physics background and understanding sensor technologies to the level of, why are these waves reflecting in this way? What kind of reflections could you be getting? And like understanding those at a very fundamental level, I think are actually very critical for good engineering. If it can be abstracted away, and meaning that you're more interested in kind of like disembodied AI is a good example. So robotics, I think about as embodied AI that needs to interact with the physical world and kind of sense it and whatnot. So there, a lot of those things become very important. That understanding of physics may not be important if you're building an AI to help you book dinner reservations or other various things. It doesn't mean that we as electrical engineering don't have to explore, learn, understand, and master a number of topics from CS. Certainly, I mean, CS is not programming, but we certainly use lots of programming. There's kind of a common requirement, I think, these days that people are build effective programming skills at four-year research universities. But it's really kind of that question, at least on the robotics side, is disembodied versus embodied. Do you worry about sensor models and you can extract those things? Can you abstract some of those things away? And I mean, there's certainly things that we don't cover as well in electrical engineering that you may be excited about. We don't do theory of algorithms as computer science does. So if you're particularly excited about the theoretical underpinnings of why search and some of these other things work, that's great. But we go into a different area of theory, like in the Kalman filtering and other parts of electrical engineering that are important for things like signal processing. So both certainly have plenty of theory, but where we distribute the theory is a bit different. But the other big difference is senior design. So senior design, we have a senior design sequence where you build a project. There is a senior thesis option, I know, here in computer science, but it is not structured as that kind of systems engineering introduction, practice, development, demonstration. And I think that's actually a really excellent thing. And it's one of the things we do pretty well here at the university.
So one of the questions, I guess it's a follow-up of the one prior to this, is that, what does problem solving look like as a student in ECE? Like, how much of work is independent? How much are you doing, with the requirement of a lab? What does the problem solving look like in ECE as a student?
It varies course to course. So some courses tend to be more theoretical, but problem solving. You're learning how to kind of represent problems as differential equations, and you're learning solution strategies that you can find, analytical solutions to those problems under certain assumptions. I think as you move further into the field, some of those assumptions tend to break down when you move them into the real world. So as you learn how to approximate those things, you may have to solve some things numerically. The example thing that my students are doing right now is they're tuning feedback controllers based on an idea of how this motor is supposed to operate. But they've built their own data collection system to be able to identify the transient response in the motor, and then they can choose gains accordingly so you get the behavior you want. My course in particular is set up, laboratories are like requirements. So it's a requirements document. Your laboratory needs to do these 7 things by the end. There's some guidance as to how I want you to sit there and do those things, or what structure I want to see. But there is some flexibility to implement the algorithms in the way that you see most fit, choose different strategies for doing it, and so on and so forth. I like to think about these things more like engineering requirements as opposed to, I'm looking for the answer is 12. So I don't know if that fully answers your question, but I think the answers become more, they become less specific in some cases you move later on, because there's more than one solution to a problem. And I think that process of actually problem solving, exploring different ideas, trying to choose, which of these avenues is most promising. And sometimes you get halfway through and you find out that was the wrong option and something didn't realize. So part of that process is what you learn here. And part of that goes on in all the courses. So.
That makes sense. A lot of the people who view the full spectrum series lectures are prospective students or parents. And a lot of them have some exposure to robotics, but what do you think is the most misunderstood part about studying robotics?
Oof, that's a good question. So the definition of robotics tends to vary a lot in terms of what people think a robot is. I mean, I tend to think about robotics more generally as this embodied artificial intelligence that has to sense the world, build a model of the world, and invert that model to make a decision. So, a teleoperated system, which is, taking human input and kind of expressing it kind of like a remote control car or other things, the level of intelligence there is fairly low level. When we think about trying to develop robotics now, it's the full stack, right? It's, you can have a robot. You can come up with some wonderful plan that inverts the model, that does a reasonable job of trying to identify what the world looks like from all these sensory inputs and whatnot, and then you put into practice and your motor controllers aren't doing what they want to do, and then your system isn't safe. So it's kind of nothing works until everything works. So it's so you kind of have to do all of it, which is part of the reason why I think this very wide cast net or wide cast background in kind of fundamental physics, system engineering. We incorporate machine learning, other things. We have a new course, a new advanced elective called the Art of Machine Learning here in our department, which I think we're excited to have students start taking in the spring. There's a lot of different parts to robotics, and it seems to be getting bigger and bigger all the time. But you can specialize in certain parts of robotics, to be clear. I mean, robotics lives in many different departments at many different universities. And I like to joke, it's actually in the department that seems to kind of historically index when the university got excited about robotics. But for here, I think it made the most sense for robotics to live here in electrical and computer engineering, although certainly collaborating with people in CS and biomedical engineering, mechanical engineering make a lot of sense. And there's lots of researchers there that do things that are important for robotics as well. But robotics is kind of broader than just building the robot, right? Building the robot is mechatronics and is something that we teach. But those advanced electives that I talked about before, that building those layers of intelligence, learning how to sense the world or whatnot, that arc is actually what completes a kind of a proper foundation in robotics, in my opinion.
One of the questions from one of the participants, can you talk about how the audio and music engineering program relates to the ECE program?
Yeah, sure. So we share a number of courses, but they tend to diverge around the second to third year. We do have students who take some of the non-required classes in electrical engineering. I have students who are AME students in my mechatronics course just because they were interested in trying to learn those things as well. But AME tends to they tend to get the same foundation in circuits, signals, signal processing and whatnot. And then around the time when the focus on semiconductor devices and integrated circuits comes in, they tend to specialize separately in signal processing and some of the kind of audio recording and whatnot specialties that you see inside of AME. So it's a bit broader. I think there's also some music requirements that we don't have as well in the program, but that tends to be where it diverges. But they also do participate in a senior design sequence as well. So it's exciting to see what they build there as well when they get to the end of the program.
Great. Another question that we have asked all the speakers in the Full Spectrum series is about failure. A lot of times prospective students or first year students have had all this pressure to be perfect and to be able to not have significant failures. But how does failure exist, or what does it look like within ECE?
Good question. I mean, we do try to make sure that we support our students through the program, but there are many opportunities or many situations where retaking a course or retaking some activity makes sense. I often tell students my assessments in my class are not about getting a score. They're about trying to identify what you need to work on. We just did a laboratory assessment in my course about a week or two ago, and it was a 2-hour programming kind of programming assignment where you get to get a set of requirements and you don't get the board to debug your solution. So you have to go through and you need to think about the kind of program you want to implement, make sure you understand reading the data sheets, make sure you understand the architecture you're implementing. And then we plug it in at the end and see if it works, right? And not everything works, and there is partial credit, so that's good. But a lot of that is trying to understand or highlight what you simply need to go back on and learn. So my goal is you understand the material well by the end of the semester, and if somebody encounters a roadblock, we work on that for the semester and we try to identify it there. So I think there's lots of different perspectives to it, but in the end, the goal is to produce engineers that satisfy both our student outcomes and the ones that we're confident can go out in the real world and be effective. So that iterative process, and grades are a form of feedback, but it's not the only form of feedback you get here. That's important. But I also think there's lots of students I work with in the lab. In fact, I just came from the lab that I was teaching in today, and they don't work immediately, right? And that's okay. It's about kind of iteratively working at it to try to get working by the end, and go from there. So I don't know if that fully answered the question, but if the question was, did I get a 4.0 when I was here as a student? The answer is no. But it's okay. It's actually good to see students kind of stretch and challenge themselves and do things which are more about learning and less about the GPA in the end.
That makes sense. One of the parts of Ed Hajim's commencement address that I really like is, he cites, hard work and understanding, what he wants, but he also talks about catching his wave, and he feels like he caught his wave, in plastics, and being able to find something at the right place at the right time. In terms of ECE, what do you think is the next big wave for someone to jump on? That is either a current student or a prospective student at this point?
It's a good question. I mean, I would say robotics, but obviously you would feel that would be biased. Anyway, let's say robotics. No, beyond robotics, quantum devices. I mean, part of our interest in trying to design the curriculum to give that foundation to all students is because it seems to be an increasingly important topic. We want our students to be prepared for that. So that's one of the directions that I think is kind of new and exciting, and you're starting to see a lot of cool work coming out of our research laboratories on some of these ideas. So there's also new work and new research in semiconductor materials and devices as well. Stephen Wu's work here is very exciting to see coming out of his lab and the work he's done. So I think at the very fundamental level, like semiconductor devices and kind of what kind of things at the small scale there in electrical engineering is one of the most exciting things we have going on. But there is exciting things in every area, to be clear. I mean, machine learning for signal processing, very exciting. There's all the issues of trying to scale up computing and trying to keep Moore's law going. So there's lots of things, but I don't know. I'll go with that for the answer.
Okay, we have a question from participant. Where do your graduating electrical engineering students often go to for careers?
Oh, good question. So a number of our students go off to larger tech companies, but some have actually gone off and started their own, which is exciting to see at various times. We have a number of students go off to grad programs. One of the things we do well here, I think, is get students ready for both master's and PhD programs, because we do both theory and practice of these ideas. I mean, for example, I've had students go off and intern or work in companies that do medical robotics and some of the self-driving car work. So there's a number of different places where I've had students go off to work based on my own background, but I've also had them go off to other grad programs as well, well prepared and doing well, happy to say.
Great. I think we have time for one more question. So as prospective parents and students watch this, and what advice do you have for them to start to narrow down their interests? Like, what resources can they start to look at to see if this is something that, one, they want to do, and two, if there's a more specific part of this that they could find?
Sure. I mean, the program is fairly well structured out in the updated EC curriculum guide. We have two. The updated one is the right way to go. I think the best way to come to a decision is kind of what I did when I was a student here, a prospective student, when I was looking at various schools, which is I had to imagine how you would spend that 4 years and how you would distribute your time. If you were spending your time doing things that you were excited about and the courses aligned with your interests, and you think that there is the opportunity or flexibility to be able to kind of pivot your interests in directions that you may find exciting that you don't even know yet, because I didn't know I was going to do robotics in high school. I had some sense, but I didn't know this is really what I was going to be doing, and I couldn't predict my advanced electives as a senior in high school as to what I would take through the program. So finding one where you feel like you're spending your time taking the things you're excited about, but also have the flexibility to pivot, I think is important. So like I said, the Rochester curriculum for me was a big draw here. And being able to do engineering with that flexibility to pursue what I was excited about was an important decision.
Excellent. Well, thank you for coming here and doing this, Professor. We really appreciate you being able to provide all this clarity. It was special for me to also think about the prospect of you teaching courses and materials that you took here
Yes.
as well. So we're glad that you came back. So again, thank you so much for being here. We are going to put this on Facebook and YouTube and Instagram for you to view. If you have any questions, we're going to put, my contact information, Professor Howard's contact information to be able to go further. Thank you again for doing this. We will be back in about a half an hour for data science on a separate link. So thank you all for being here and have a great weekend.
Thank you.